we will continue with our discussion on candidate blackbody distribution functions. Okay, in the last class we looked at some of the candidate blackbody distributions like the Jeans distribution and the Rayleigh-Jeans distribution, both of which failed in different parts of the spectrum in the sense that they did not agree with the experiments fully. That is, in certain portions of the electromagnetic spectrum they agreed, in certain portions of the electromagnetic spectrum they diverged or deviated from observed blackbody behavior, and the Rayleigh-Jeans had a fatal deviation from the experiments at shorter wavelengths. This was basically called the ultraviolet catastrophe because it happens in the ultraviolet portion and beyond, but there is controversy in literature regarding the, you can google this ultraviolet catastrophe and see why this name has come and whether Planck really worried, I mean did Planck try to do curve fitting and try to see why Rayleigh and Jeans is not matching, or independently he developed the quantum theory and then after some time he figured out that other people also got the incorrect distribution and so on. But to put it in historical perspective, it is good to proceed with the argument that Planck looked at all these distributions and found out they are not agreeing, then he added 1 minus 1 and then in the denominator and then it agreed, then he found out with classical physics, that is Maxwell-Boltzmann statistics, it was not possible to figure out the correct distribution, therefore he proposed a quantum hypothesis, right. And then we saw that one was in 1900, one was in 1905, but Planck's was in 1901, and after 1900 and 1905 these Rayleigh and Jeans, okay, they published their findings. 1900 in the same journal philosophy magazine, Lord Rayleigh had published the same result. After 5 years the same result has been published in the same journal, and but in between Planck had published the correct result, not in the same journal. I think it is not in the same journal, but it was known that by 1905 it was known that this was not the correct distribution because it was deviating, but still they went ahead and published. So there are so many, I mean a lot of controversy surrounding the birth of quantum mechanics. Now in today's class we will derive the Rayleigh-Jeans distribution. First we will derive the Rayleigh-Jeans distribution, and then there is some commonality between the Rayleigh-Jeans as well as the Planck distribution, and many of the steps are the same, but the critical step where we look at the average energy of the oscillator, then there is a deviation. There will, in tomorrow's class when we derive the Planck's distribution, then we will make appropriate changes and finally get the famous C1 lambda to the power minus 5 divided by e to the power of C2 by lambda t minus 1. In today's class we will derive the Rayleigh-Jeans distribution. It involves some very tricky mathematical steps and all this. Pay attention, you may not be able to follow all the steps involved generally because this is all lifetime work, Nobel Prize winning work and all that, we are trying to do it in 1 hour, but you should be able to get an overall gist of the whole thing. But if you want more detailed derivations, you are encouraged to look at, not at radiation books, no radiation textbook will give all this, you have to look at some books in modern physics, Arthur Beiser or some other books. If you look at modern physics they will derive all these equations, okay. I am not sure whether you will understand fully, but the material would have been presented in many of the physics textbooks. Now let us look at radiation field enclosed in a box. It is a cubical box, it is of size A, so the volume is A cube, okay. We are looking at stationary waves within this box and the radiation field is enclosed within this box, okay. Now the goal is to find out what is the radiation energy density within this box, okay. If you get the radiation energy density within this box, that is U, okay, then you know the relationship between U and I, right. So if you get an expression for U, then you will get an expression for I, and that is basically the Rayleigh-Jeans distribution. So the effort goes in determining the radiation energy density. When you are looking at waves, then you have to find out what are the possible number of waves between a frequency nu and nu plus d nu, okay. If you are considering a frequency nu, consider a small interval d nu about this nu. Between nu and nu plus d nu, what are the possible number of, I mean it is like possible number of modes of vibration, the possible number of standing waves. If you get the possible number of standing waves, okay, for this cubical volume multiplied by the average energy per frequency or average energy per frequency, I mean average energy for each wave multiplied by the total number of waves, and divide it by the volume of the container, which is A cube. So you have a spectral radiation energy density. Are you getting the point? From classical physics, every harmonic oscillator has got 2 degrees of freedom. One is a kinetic energy and one is a potential energy. Okay, and you know from we know from Boltzmann statistics that the energy associated with the kinetic energy is half kT, and the energy associated with potential energy is another half kT. So kT is the average energy. Okay, if you multiply by the number of waves, number of possible waves between nu and d plus d nu, then you have got the numerator. The denominator anyway is A cube. Then you have got an expression for the radiation spectral radiation energy density in terms of nu, that is u nu. From u nu you can get I nu. Then the relationship between u nu and I nu is basically like is it correct? But I have to put a when d nu is positive, d lambda will be negative, isn't it? Okay, so but C is equal to, so nu is equal to forget about the sign. Okay, I nu knowing fully well that I am ignoring the minus sign. Okay, did I make a mistake, Deepak? Instead of watts per meter square per micrometer steradian, I can also work with watts per meter square per steradian into what are the units of frequency? Hertz. So how do you convert watts per meter square per hertz into steradian into watts per meter square per micrometer into steradian? Because why I am specifically doing this is, it is easy for me to get I nu first, and suddenly when I am doing the derivation, suddenly I change I nu to I lambda, you should not get confused. So I am writing this up front. I will also do it when I do the derivation. Are you getting the point? So this is the relationship between I lambda and I nu. Okay, so if you get I nu, you are home. Okay, in fact you do not even have to get I nu. What is the relationship between I and u? U is 4 pi IB by C. So if you 4 pi IB by C, fine. So if you get u nu, then you actually solve the problem. From u nu you can get IB nu, from IB nu you can get IB lambda. That IB lambda, you know the result. What is the Rayleigh-Jeans? C1 lambda to the power of minus 5 divided by C2 by lambda t. Now it is 1110. By 1150 we have to derive this. Okay, so that is the story. Now so Lord Rayleigh and Jeans, they must have spent years in trying to get this, okay, because the result was not there at that time. We are trying to understand what other people have done, but they tried to create this, right? So there is a lot of difference. Okay, now consider a radiation field within this box. Okay, now let us assume that the box consists of what kind of waves you will have. All the walls of the container are closed, impermeable. Yeah, it consists of stationary waves or standing waves, right? So now we have to find out the allowable frequency modes, the allowable frequency of the waves. This can be obtained on the basis of resonance theory and kinetic theory of gases. Okay, so now monochromatic this is an alternative terminology for spectral. Monochromatic is equal to number of waves into energy associated with a wave divided by the volume of the container, correct. What is the volume of the container?
Cube.
A cube, very good. What is the prescribed frequency? Between 1 gigahertz and 1.0001 gigahertz, how many waves are there? Okay, something like that we are doing, that is the d nu. Okay, now what is the energy per wave? Half kT this is for kinetic energy, this corresponds to potential energy. What is K? K is the Boltzmann constant. Boltzmann constant already existed because Boltzmann figured it out first. Okay, K to the power minus 23. Tell me the units. Joules per Kelvin, correct. Yeah, joules per Kelvin into Kelvin will become joules, right? That is energy. The unit of energy is joules. Okay. This is nothing but U nu. From U nu, I know the story. U nu can be converted to I nu. I also know how to convert I nu to I lambda. There are three things involved in this U nu. Two quantities in the numerator and one quantity in the denominator. Denominator is volume A cube, I have found out. The other quantity in the numerator is the energy per wave, that also I know. Now getting the Rayleigh-Jeans distribution now boils down to getting the number of allowable number of waves which are possible between the frequency nu and nu plus d nu. This is not so simple to get. Okay, so we have to go to the 3D wave equation. Okay, to get that number you have to go to the 3D wave equation. Okay, so we have to go through the mathematical development. We have to use a 3D wave equation which is applicable to standing waves which are moving around in the container. Okay, now 1 by c square shall we start with 1? This one will start as 1 plus psi is the wave function. Okay, psi is the wave function. So it is a electric for an electromagnetic wave. For an electromagnetic wave, psi represents the electric or magnetic field magnitude. Okay, psi is the wave function. don't worry, I am not going to derive fully the equation, the solution and all that and apply the boundary conditions and use the method of separation of variables. We have to get the most pertinent quantity of interest is the frequency. We'll pull out that frequency, that is the number of possible modes, okay, of number of possible number of waves, the number count of number of waves with a particular frequency. If we get that, then we can ditch the 3D wave equation. We don't have to worry about it fully because this is not a course on quantum mechanics or statistical physics, that is not our intent. But we need to know how to get the number of waves with a prescribed frequency, whether it is 1, 2, 3, 4, 5, 6, 7, 8 or how can it be related to other quantities of interest. Okay. I would expect that the radiation energy density, because the radiation energy density should be independent of the container. If a bigger container gives me different radiation energy density, Rayleigh-Jeans distribution will be dependent on the size of the container, which is far from the truth. I know that it is not correct. Therefore, I expect that the number of waves will be a function of some term A cube will be there, so that in the denominator I will remove the A cube volume, so that U nu becomes independent of A, correct. So when in my development of this wave equation, that A will come, it has to come because the boundary conditions are applicable at x equal to 0, x equal to A, y is equal to 0, y is equal to A, z equal to 0, z equal to A. Are you able to see the connection? No? The radiation spectral density should be a function of A. Density of material is dependent on the volume of the material? Or? Yes? The mass of the material is dependent on the volume of the material. We talked about intensive and extensive properties in thermodynamics. Okay, if you suppose the air is homogeneous, if you take some volume, if you calculate the density, you take a bigger volume which is twice this, you get twice the density. No, therefore the U nu must be independent of A cube or A, right? The denominator has got A cube. Energy is not a function of A, therefore the number of waves must be some A cube must come there. Now in this wave equation there is no A, but after all this wave equation is applicable to that box. Through the boundary conditions the A will come in the solution, you should intuitively expect. So some A cube will get cancelled somewhere, otherwise we are in trouble. Okay. Now what sort of equation is this? What sort of equation is this?
Poisson equation.
Second order difference is okay. Is it a PDE or ODE?
PDE.
Okay. It is a PDE. Then it is a hyperbolic PDE. Okay. You have to get the equation of characteristics and find out b square minus 4ac for a second order partial differential equation, b square minus 4ac less than 0, equal to 0, greater than 0, depending on whether it is less than, greater than or equal to 0. You classify PDEs as elliptic, hyperbolic or parabolic. This is not a mathematics course again. If you have doubt, go to Google or Wikipedia or take any maths book, you can figure it out. It is a hyperbolic equation. Okay. Now this can be solved using the method of separation of variables. Okay. It is a linear PDE or non-linear PDE?
Linear.
It's a linear PDE. Okay, a non-linear. Again, the fun doubt arises. What is the difference between a linear PDE and non-linear? The Navier-Stokes equation on the left hand side, you got u dou e by dou x. Okay, that's a non-linear. That's a non-linear term. Why it's non-linear? Because it can be treated as dou by dou x of u squared by 2. So it is depending on u to the power of something, right? U dou e by dou x is dou by dou x of u square 2u du by dx divided by 2. Or in a differential equation is u is what you want to find, that dou e by dou x is multiplied by the u itself, that becomes, if it is x du by dx it is okay, but if it is u du by dx it is not easy. and then v dou e by dou y, it becomes, that is why so much of effort is spent in trying to solve the Navier-Stokes equation. Fine. Now I can it can be solved using the method of separation of variables. The first step in the method of separation of variables is to assume a product solution. Okay, assume a product solution. So psi equal to t of t, x of x, y of y, z of z, 3. I hope somewhere in one of the earlier courses you have solved some equation, either the heat equation or the Laplace equation, using the method of separation of variables. Now, what are the boundary conditions for this problem? So for stationary waves, for what are the boundary conditions? These should be two equations, but we can keep it as only one. How many boundary conditions? How many boundary conditions does it support? 6. 2 on x, 2 on x, 2 on y, 2 on z. How many conditions are required with respect to time?
2.
2. Either you say psi equal to 0 or t equal to 0, and right you tell the story about dou psi by dou t. Or if you know at some other time, you can say, usually we know the information about psi at time t equal to 0, that is called the initial condition. So since it is second order in time, we require 2 initial conditions or 2 conditions on time and then 6 conditions in space. Okay. Now similarly psi equal to 0, we do not have to worry about the conditions with respect to time because we are not trying to solve this. I will get an expression for frequency. I am looking at the frequency, I will relate it to the number of waves in the cubical container, y equal to a so what is the solution to this equation? Your guess. Yeah, so solution will be psi will be equal to, or psi n will be equal to correct into of course why should the n be the same, so it should be n1, okay, where n1 n2 n3 are arbitrary integers, they cannot assume fractional values. This can be verified, you must have studied the solution to the wave equation, right. So n1 n2 n3 are integers. What is omega n? There is a wave with a omega n is multiplied by time, so omega must be a frequency. So what omega means, what type of frequency? Circular frequency, right. Omega n is the circular frequency. So what is the expression for the circular frequency? Omega n will omega n square okay. So 7 8 okay, it is called the circular frequency. Omega can be, omega is equal to omega in terms of nu 2 pi, correct. Yeah, please get an expression for nu n. C by 2a, huh?
1 by 2 pi.
Root of n1 square plus n2 square plus, correct. So we have achieved some limited success so far. We looked at the mathematical development of a 3D wave equation, and then we wrote the general hyperbolic PDE. We got a general solution, and then we didn't solve it fully, but whatever we wanted was the expression for frequency, then circular frequency, then we put it in terms of nu, and then we got nu n is C by 2a into n1 square plus n2 square plus n3 squared root of. Now we are left at this stage. Now how do we proceed further? We want some number, right? So what is the challenge now? The challenge is to come up with an expression for the number of these discrete frequency modes that are allowed between that are allowed in a frequency interval nu to nu plus d nu, and then you got and then you can go home, you are home. But now you got some n1 square, n2 square, n3 square, it is more confusing than our starting point. So something we have to, in order to do this, we have to look at some analogy. So we have to do some number count, right? The number of discrete modes for these waves which are allowed between a frequency interval of d nu, between nu and nu plus d nu. For that we will resort to geometry, okay. We will use some analogy, okay. So can we make it bigger, or? Consider a situation like this, okay. n1, n2, n3 can take on integer values, and n1, n2, n3 all have to be positive, right, okay, fine. Now let us consider a 2-dimensional situation where you have got unit squares, okay, where you have got unit squares. I am looking at a differential area, 2 pi r dr in the first quadrant, okay, and the n1 and n2 are just like these two numbers. We have n1, n2, n3. I am doing a 2D representation of this, okay. So this is 1, 2, 3, 4, 5, 6. Now let us consider we are starting from 0, 0 here, okay. This is all unit radius, okay. This is, so therefore here we have come up to, this is 8, okay. So that is, it is between, right, it is between 7.5 and 8.5, okay. What will be the area? Look at the figure. Everybody has this sheet, okay. Hatched area, see, this is not the only way of proving the Rayleigh-Jeans distribution, but I thought this is very intuitively appealing. some other physics book may deal with it differently, but I thought this is easier for all of us. What is the hatched area? 2 pi r dr. What is dr? Dr equal to is everybody convinced that dr equal to 1? Because unit square I am taking. So what is 2 pi r dr now? Tell me, r equal to 8, please calculate.
4 by
2 pi r dr by 4 because it is a quadrant. Everybody is, when I say 2 pi r dr, nobody is opposing me. It's 2 pi r dr by 4. 2 pi r dr is the full thing. How much? What is it? So what are you getting?
12 point.
12 point?
12.56.
Why is it so difficult? 12.6. 12.56. What is this elementary geometry? What is a big thing? The beauty is, count the number of lattice points which this hatched area cuts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if n or r is sufficiently greater than 1, the area of the quadrant is exactly equal to the number. But what we want for the spectral density is the number of waves. So the number of waves can be related to the area. But here we had only n1 and n2. In an actual case, we will have n1, n2, n3. Instead of a quadrant, we will have an octant. Of the sphere, the first octant, if you are able to figure out 4 pi r squared dr by 8, that is exactly equal to the number of lattice points. That number of lattice points is the number of waves which are allowed between a frequency of nu and nu plus d nu. Is it okay? Right. So number of when r is much greater than 1, these two will agree exactly. So we are not home yet, okay, but we are going in the right direction now. Now the radius to any point Rn is given by root of n1 square plus, correct? So in your coordinate system n1, n2, n3, root of n1 square plus, just like root of x square plus y square plus z square. Put some equation number. So what we are now trying to do is, in order to get this, let us think of these discrete frequencies in terms of a space lattice, and we are counting the number of lattice points having unit dimensions. That's what I have done, but I have done it for the 2-dimensional case. Now the number of points having a distance, therefore given by equation 9. You are convinced, right? In a 2-dimensional case, the number of points which are between r and r plus dr can be easily counted by not doing a number count, but by just taking 2 pi r dr by 4. Therefore the number of points lying between r and r plus dr in a 3-dimensional in a 3-dimensional lattice space is given by 4 pi r square dr by 8. Instead of 2 pi r dr by 4, we have 4 pi r square dr by 8. So the number count was analogous to the area, elemental area in the case of a 2D, it is equal to the elemental volume in the case of the 3D. Which one? Good. Which one? Dn is elemental. No, it's still elemental. Yeah, but we will take that elemental and divide it by the elemental a cube and then we can proceed. That is a representation, right? Because 2 pi r dr is also elemental. Okay, right. So when r is much greater than 1, this can be visualized as the number of lattice in the volume of an octant of a spherical surface having a differential thickness, correct? Since the number of lattice intersections corresponding to the number of unit cells, if we say something like that you will get confused, but you have already understood, right? So we can so this is the terminology used by those guys, right? Now from Rn is equal to 1 into then we had dn is equal to 4 pi please remember that we divided by a 1 in the denominator because it was unit radius, right? Because the numerator has got units of volume, denominator also has to be by volume because the left is just a number. Volume can never be equal to the number. For illustration I told you unit, that means I am dividing by 1 into 1 into 1. Okay, please remember, but now your Rn is C by 2a root of so Rn is equal to C by 2a, correct? This is what we got, right? We already got this. Therefore dn nu must be equal to 4 pi nu squared d nu divided by 8 into what should you divide by? C by 2a whole cube, right? When it was 1 into n square plus, for a 2D case, if it is Rn is equal to 1 into n square plus n2 square, the dA was 2 pi r dr. When Rn is equal to 1 into n1 square plus n2 square plus n3 square within root, it is dn equal to 4 pi r square dr by 8 into 1. That 1 is corresponding to this, but now we already derived the circular frequency nu n is equal to c by 2a root of n1 square plus n2 square plus n3 square. 15 minutes ago we derived this. Therefore it will be 4 pi instead of r I will have nu squared, r squared is replaced by nu squared, dr is replaced by d nu, I divide it by 8 and instead of 1 I have to do c by 2a because c by 2a is multiplying the root, is prefixing, alright. Okay, now what is dn nu now? Now please get the expression for dn nu is, so dn nu 4 pi a cube, agreed? All these you can keep in brackets, they are not central to our, this is only for understanding. It would have been terrible if I told you that the elemental number of possible wave modes is given by this. How many of you would have understood? That is why I used the 2D analogy. We did the number counting, I extended to 3D. Instead of multiplying by 1, I multiplied by c by 2a and all this story. Now therefore, so I will take only this, anyway my d nu was equal to 1, okay. Now I will take this u nu is Ah, A cube is gone. A cube is gone. Okay. Now, what is the equation number? What is the equation?
13.
13. Good. So u nu equal to 4 pi nu squared by c cube into kt. But two possible directions need to be considered. It is an electromagnetic wave. What are the two types of polarizations which are possible for an electromagnetic wave? E parallel and E perpendicular. Electromagnetic wave, correct? Electromagnetic wave. What are these? Called E parallel and vertical polarization, horizontal polarization. Therefore, u nu must be into 2. Because there is an additional degree of freedom which is allowed. So it will be 4 pi nu squared by c cube kt for the horizontal polarization, 4 pi nu squared by c cube kt for the vertical polarization. You add these two, right? Now you got u nu equal to 8 pi nu squared by c cube kt. So what is the relationship between u nu and I nu? Therefore IB nu equal to, can you help me out? IB nu equal to
C by 4 pi.
2 nu 2 no, we are getting stuck. 2 nu squared by, correct. Okay. What is the relationship between I lambda equal to IB lambda equal to IB nu into correct, C by lambda square or lambda square by C, don't make it will be terrible otherwise. Please don't let me down. I am not recalling from memory, I am also doing with you. Okay, so therefore IB lambda equal to, yeah, tell me, 2 nu square by c square. Nu can be written as c by lambda, right? C cube, is that correct? Yeah, if I made a mistake, you just tell me. Fine, very good. I can make it C naught, okay? I am multiplying, I am dividing by, okay, so IB lambda by two h C naught square What else is remaining? Huh?
KT by C naught.
KT by HC naught. Which one? H is the Planck's constant. No, it is not now, but people know the first radiation constant and the second radiation constant. The 2h C naught square is the first radiation constant C1. Okay. So now h C naught by K. So okay. Now what do you get? H C naught by K is C2. Now can you put the IB lambda? So we are home in 50 minutes. This is the Rayleigh-Jeans distribution. Of course, he didn't know that 2h, he got some all this and okay. Now this is called the first radiation constant, this is the second radiation constant. It's fine. So I think it is you have to go through, you have to go back to your hostel and then go through this couple of times. Okay. It is not so easy to follow this, but it is without any blemish. It's everything is correct in this. You will have to understand. If something something is bothering you, you can come and ask me. So we first derived the incorrect distribution. In tomorrow's class, we will derive the correct distribution. That is the IB lambda Planck. Okay. So this is our number counting, right? This is Lord Rayleigh, 1842 to 1919. He proposed a black body function 1900. Nobel Prize 1904. Sir Jeans, 1877 to 1946, he proposed a black body distribution in 1905. Both of them published in the same magazine called journal called Philosophy magazine. This is a guy with a short name. So Wien proposed a black body distribution 1896, Nobel Prize 1911 for radiation. All these people are getting Nobel Prize in radiation. Okay. Then finally Max Planck, 1858 to 1947, he proposed a black body distribution 1901. He got PhD at the age of 21. Okay, in 1879 he defended his PhD on the second law of thermodynamics. Okay, Nobel Prize 1918. Okay, on that note we will close the class with picture of Planck. So Max Planck, the ultimate Max Planck. Okay, so we will meet tomorrow. So tomorrow we will see how this man figured out the distribution. Okay.